Okay, good afternoon and welcome back. Uh, we will have chapter 2, but and before that, I want just to have a review on the previous lecture. We talked a lot about the first step of supplying water supply, and it was starting from the screen bar. So before that, let's show you the the one that we have it in Suleimania water treatment plant. This is the Suleimania water treatment plant. Actually, this plant is close to the river, close to the road that is beyond the river. Means if this was Kashkoli River, so this is Kashkoli River. So there is a street, and there is an intake here. This is an intake structure here. So the water is coming to this intake, and then it will be delivered where it will be delivered here. So okay, yeah. So there is an intake here, and this intake will send water to the main. This is water treatment plant. This is called the first unit of the water treatment plant. So the intake is a structure that are located for having water. So to deliver water from the river or any kind of rivers like dam and things so. There will be this intake, there will be a kind of pumps here, and there will be there will be a tank. It's called sump tank. Then the pumps are stay in this sump pumps, and they will receive water from the river and then send it back to the water treatment plant via this pipe. This is called raw water pipe. Okay. Now we calculated how to find the capacity of this treatment plant, because the capacity of this treatment plant will means the capacity of the how much needed water is for to be supplied to the city. For Dukan water treatment plant, its capacity about 12,000 meter cube per hour. And this dash lines are for the second stage, not for now. So these 1, 2, 3, 4, these are already there. These are already designed, and these are already constructed. But the following dashed line are to be for the future expansion. We said that we need at least to have 30 years design period. So what should we do? Shall we start with all the structure in one in time, or we can manage our work step by step? So now they started, in 2008 they started with working in this. 2000, I think 6, they started working in this project, and 2008, 2009 they finished these items, 4 tanks here, and all these are stay for the future expansion. My point is, the first item or the first step for treating water is to have water from the raw water from the intake structure. So this intake structure will be the first structure that will help us, and let's see what will include, what this intake structure will include. This structure will include, first of all, it's a kind of chamber or channels, and these channels will have a screen on it. So these screens are called bar screens, we have bar screens, so we have mesh screens. What is the difference between bar screens? Bar screens are usually rods, and they should make, sometimes they are circular shape, sometimes they are in a square shape. So they will be put it in this way, and there will be another one beside that one, and these are aligned in intake of this channel, and the water will come inside this channel. This is called screen, and this is called bar screen because they are almost, but we have bars here. And now we have another one, we have mesh screens. What is that mesh screen? The mesh screens are both both bars will be look like this and will be look like this, vertical bars and horizontal bars. So they are both together making a mesh or grids. The mesh screens are will be like this. There is another third one, which is which is called moving screen. Moving screens, we have drum and we have belt screens. Now, a quick property for these screens are, we have bars, which is called coarse bar screens. We have middle bar screens, and we have fine bar screens. What is the difference? It's all about the space between the two bars, two adjacent bars. If the space, the opening is called, was to 2.5 centimeter or greater, then it's called a coarse bar. And if it was between 0.6 to 2.5 centimeter, this is called middle. And if it was less than 0.6 centimeter, the space was less than 0.6 centimeter, then it's called a fine bar screen. So the fine bar screen are having space between the bars less than 0.6 centimeters. Now, what is the mesh screen? The mesh screens almost, we have the space. We have two types of the space, horizontal space, and we have vertical space. So usually this is a square. It will be a square, and the space or the opening will becomes between a bar and another bar. They are the same, and they are varied from 1 to 25 or 2.5 centimeters. And there is the main thing that the difference between the bar and mesh is, for the bar screens, the velocity of the flow or between the bars. This is the bar and this is another bar. So the water is coming between them, and they will make velocity between them should be between 0.3 to 0.6 meter per second. While for the mesh, we should have less velocity of water. But why? Because we don't need to do obstacles to stack on this one, and besides of that, we have more velocity, means more head losses, means the water can lose its energy. And this is was as we have in the previous chapter. And also we have another three types, which is moving screen. Moving screen, sometimes we have belt screens. Belt screen means that it will be rotated, and we have a drum, and the drum screen will be allocated for the not having area space. Do you have any question about these screens? And we solved an example on how to find them and how to design the number of the bars of the screens. Now, after we have a screen here, there will be a pipe. This pipe will deliver water from the screen and send it to another tank. This tank is usually concrete damped, and we put water pumps here, and this water pump sends it to the water treatment plant. Now, So what is the rule of this sump is just to collect water, receive water from the screens. And we have sometimes we have submerged intake. It means the screen is under the level of water, and sometimes else we have another kind of intake which is called tower intake. It will look like we have a tower inside the water, and the water is coming inside this well on that tower, and we will deliver water from this tower and send it to another tank which is called sump. And then this sumps, we have pumps from this sumps, and it will go to the treatment plant. Other types of intakes we have pipes, we have this screen. Look at this one. This is a sectional view, means this is a section. This is a bar screens. Bar screen, it means the water is coming in this way, and it will be filtered, and then there will be a pipe. This pipe will deliver water from this intake and will put it here. Now what I will do here, I will put a pump here, and this pump will send the water to the first unit of the water treatment plant. And this is the elevation section, and this one, it will be the cross-sectional view. Now in this, today we are going to solve, or we are going to design how to design this part and this pipe. So the screens are, we know how to define them, but we should know how much is the number of the pipe should be laid in this part, and how much is the volume of this tank. Now we have some key design points. We should take care of them, and then start solving the problems of design. Now, as a designer, you have to take care that this kind of structure, or the sump intakes, will be based on the demand of water. I mean by that, how much is the capacity of the water treatment plant that we will have. There is a theory for the design, and there is a theory for the check. Usually the design for any structure that you will have, the design will be for the future. It means that if you are a designer, you have to design your structure for the future. It means after 35 to 40 years. This is called design period. But when we are going to analyze the existing one, I'm going to analyze or checking. The checking will be for the present. Now, for now, I have to check the structure. Those two most important criteria that we will have, we should take care of our career. Now, what should I do? These pipes usually should be more than one, and also more than two, because usually one is not enough, and two, it will be okay, but if in case that you have one of them out of surface, so you need to have another one free. So starting from two and plus the emergency or plus standby. Now, what I mean by the design, I mean to know how much is the diameter of this pipe, and I need to know how much is the volume of this tank. Now, what should I do? First of all, the diameter of any pipe can be found within this way. Diameter is equal to, by diameter, I should find area of each pipe. Now, what I mean by area, I mean by d square over 4, right? So this is area of one pipe times n. So this is the number of the pipes that will receive water from the rotor to the tank. How many number of the pipes? There will be n numbers of pipes. So the total number of the pipes having the n times pi d square over 4, the total area of the pipes. Now, we have the flow or the velocity through those pipes. We have to be limited. There is a limited velocity. What I mean by that, there is a v minimum, there is a v maximum. What the v minimum is, it's 0.6 meter per second. And why is 0.6 meter per second? We don't want to have a pipe with the flow inside it very little, because of what? Because you know, this is a raw water, and in the raw water we have settlements, we have suspended salts. So those suspended salts should not rest in the pipe, should not clog the pipe. So they should be called self-cleaning pipe, self-cleaning velocity. The velocity of the water in this pipe should be more enough not to let the precipitate settlings to be precipitated in this pipe. The second thing that we have, it will be should be less than 1.5 meter per second. This 1.5 meter per second means we don't have to have a turbulent flow. Turbulent flow, it will be usually it means the, you know, by Reynolds number is equal rho Vd over mu. So when we have high value of V, it means that I'm going to have a Reynolds number more than 4,000, means you are going to have a turbulent flow, which is not, let me say, suitable for this case. Now, this is the second thing. The third thing that we have emergency. In case that emergency case, it means let's have a turbulent, but this will be for a while, for a couple of seconds or minutes. This is in case that one of the pipes are broken. So what should we do? We should send emergency flow, and we should cover that one. Now, in that case also there is a V, it's called emergency or maximum of them. It should be less than 2 pi per meter per second. So these three numbers of the velocity, V should be V minimum, and V maximum, and V peak. And these should be greater than 0.6, less than 1.5, less than 2.5 meter per second. All these are the key points. Now, when you are a designer, you should assume one of these ones. Now, having a V and having a Q, so Q is equal to V times area. And now, I have this one, I have the Q. So what's left for you? Area of the pipe. So it's equal to Q over V. Now, when I have the area, it means that I have this one, and this one, and the number of the pipes, and pi d square over rho. So what's left for you? You have to assume a diameter and the number of the pipes, you will get the area. And you have to adjust between these two ones. 2 pipes with small pipe with diameter, 3 pipes with smaller pipe diameter, and so on, just to cover the conditions. This is in general. This is what we have. Now the question is, when I have to have a minimum velocity, and when there is the design, this Q should be where? This Q we have to design based on which flow. We know that we have average demand for the pipes, average demand for a city. The average demand is equal to what? You can tell me. Hello guys, are you there? Nobody there? Akar. Hello.
Yes.
Yes. So my question is, in case that you have a city and you want to design, so we know that we have an average flow rate, an average consumption rate. For example, we say that we have for WHO recommendation that everyone can have 250 liter per capita per day. This is as an average, right? So,
Okay.
yeah, this is called consumption rate. This is average consumption rate. What I should do if I want to see how much is the maximum or the peak consumption rate, I will multiply this 250 by a factor. This factor is called peaking factor, right? This peak factor will give you a maximum consumption rate. This peak factor is equal to 180 times t to the power minus 0.1. So in case that you are having average, this is per day, so you substitute t by 1, so the result is 180%, which is 1.8. So I will multiply the 250 by 1.8 to get C maximum. Okay, now in our design for this sum, we have to focus on I think it's called maximum flow rate, and which maximum I should use? I should use Q maximum monthly. Q maximum day. So Q maximum monthly, it will be used for the design of intakes. Means that what should I have to do? I have to find the Q average monthly. Then I will multiply the Q average monthly by peak factor to get the Q maximum monthly. Now, the peak factor for the maximum monthly is how much? Peak factor for maximum monthly occur, it will be equal to 180 times a factor power 0.1. Am I right?
Yes, but we should you should put the T, I think.
As T as equal to how many days?
365
This is a
or
year.
12.
No.
30 days.
Now this, yeah, that's correct, but I'm not asking about maximum yearly. I'm asking about maximum monthly.
So 30?
Maximum monthly, so T should become 30.
30, yeah.
30. Now
It's
you can check
1.28, sir.
here. So let's check this number. 30 power minus 0.1 will becomes 0.71 times 1.80. It's equal to about 1281, which means 1.28. So what I have to do, I will have to find the Q average monthly, and then this Q average monthly multiplied by 1.28 to get Q maximum monthly. So then this one will be used in our calculation. Okay. Now there is a steps for starting to find this one. Usually, for more accurately, they will use 1.28, 1.31. They will be using 1.4. So this 1.8, by experience, they found that it's better to use 1.4. Now, the design steps for having the intake pipes, intake conduits. Now, how to design this one? It means by this is the top view. Look at it. This is the top, or let me say this is the pipes that we have here. How many number of the pipes is there? So the question is to design the pipes. For designing these pipes, we have to follow the following procedure. First of all, we have to have the queue. Which queue? It's called designed queue, the design queue that we need to have it. Why we need to have a queue design? The queue design divided by area, can get the diameter of the pipe. And if I have the diameter of all pipes, for example, if I have two pipes, so a number of one pipe times an area of one pipe, this is will come area total, and then we can find from this relation we can find the diameter of each of them. So the first step is we have to find the design maximum monthly QM dot M. It means maximum monthly. This is the key one that used for the design. And we said this is how to find this maximum monthly. It will be Q average times 1.28, and from the experiences we are using 1.4. So this is Q maximum. And what should I do? This is as a maximum. There is a minimum. There should be a minimum. Usually you have, as a designer, you have two, maximum and minimum. What is the minimum? It will be the average times 0.7. So we have 2 points, two very important points. Q design will be 2. Either it will be Q maximum monthly or it will be Q minimum. So what is the Q minimum maximum monthly? It's equal to Q average times 1.4. What's the Q minimum? It will be the Q average times 0.7. Which average I mean by this? I will mean by the average monthly. Okay, average monthly. Now we need to know these two Qs. And by the way, look at this one: population times water consumption, average water consumption per month, and times 1 point. Now this is the values of the velocity that will be used, or it will be used for checking. Diameters of the pipe. Usually the number of the pipes that used in this design should be more than 2. What I mean by 2, it means the water will have to go from, this is the river and this is the sump. There should have at least 2 pipes. These are pipes. So the water that the pipes that convey water from this river to this tank, they should be usually more than 2 or more. Now, what are the diameters of these pipes? They are usually will be put it in this way. They will be the starting diameter will be 8-inch or 200, or it will be 300, 350, 400, 450, 500 millimeters. So this is per design. Yeah, it means that you don't have to put a diameter 250. They should be 200, 300, 350, 400, 450, and 500, or more 100, 550 or 600, and so on. So these are the usually used standard pipe diameters. Now, what I have to do, the steps, first of all, I have to get the maximum monthly and the minimum, Q minimum. How to find it? C times population times 1.4. This is population times Q design. So the Q design times 0.7, I can get the 2 Qs. Now this is the first thing I am done with the Q. Now the second thing is the velocity. We should assume a velocity which should be 1 to 1.5. This two dots, it means 1 to 1.5. So I will assume a velocity within the range. Means what? This assumption will be checked later. Now, when I have a velocity and I have a Q, so exactly I can find the area. Area is equal to the Q divided by V. By the way, the required area should be sufficient for the maximum monthly, right? Now, in this way, I will get the area. This is the total area, the total area of the all pipes, which means if I have one of the pipes diameter is pi d squared over 4, and then multiply this one by n, I will then have all the pipe diameters together. Now, I will assume an n and phi to check this area. So sometimes you may need three of 200, three pipes, and a pipe of each of them is 200 millimeter. Or you can say I will use two pipes with each of them 300 millimeters. So this is N, this is D, and they will be used again to recheck the velocities. How to check the velocities? We have to check the velocity within this um, within this procedure. V actual is the Q maximum monthly divided by the total number of the pipes and the area of each pipe, and this should be between 0.6 to 1.5. Minimum velocity means that you have to use the Q minimum here and also the number of the pipes here. Emergency maximum is equal to maximum monthly but divided by n minus 1. What that n minus mean? It means that if you have three pipes, one of them out of surface, so the load will be distributed along with the other two ones. In case that one of the velocities are not correct, so you have to increase one of the pipes or decrease. Is it that clear? Now, for more clear, I will look at this. To be more clear, we will solve an example on this. Look at this one. It says that we have an intake. We want to design an intake for a water treatment plant serves 200,000 capita, and the average water consumption is 200 liters per capita per day. Okay, so the question is how many the pipes that we need, the intake pipes. As I said, the average design Q is equal to population that we have times 200 liters per capita per day. So the population 200 capita and the consumption is 200 liter per capita per day. This is liter per capita per day. Per day, this will become per second. Okay, 200 liter, this is liter divided by 1000, it will become meter cube. So 2000 times this number, it will get you meter cube per second. Do you have any problem with this calculation till now? Yes? Hello? Ali? Ali? Ali, can you hear me? Berham, are you there?
Yes, sir.
Do you have any problem with that one? That
No,
calculation?
it's okay. No, it's okay.
So just we multiply the population by water consumption. And we convert the units to become meter cube per second. Okay?
Okay.
Now, this is called Q design, Q average. This Q average, when it will be multiplied by 1.4, I will get this number, which is called maximum monthly. Okay, this Q average, which is again it's 0.463 multiplied by 0.7, it will be 0.324 meter cube, and this is called Q minimum. So now we have three Qs: Q average, Q maximum, and Q minimum. Okay. We say that after this, I will assume there will be a flow through the pipes. The velocity of the flow through the pipes will become, should be between 1 to 1.5. meter per second, and then you can now I use 1.4 meter per second. This is as a trial. Then it should be checked. So if I have V equal to 1.4, so you know that the area of the pipes, F area is equal to Q divided by V. What's Q? The Q average monthly. Here's the average monthly point. This is will be mag average. It will be 0.648 divided by V, which is the 1.5. This is will be meter squared, meter cube per second. This is will be meter per second. So the result is will be in meter square. So 0.463 meter square area space needed for the water to come from the needed area. We need this water will come here. How many? It's 0.463. This is the whole area of the whole pipes. So if I have n is the number of the pipes in this section times the area of one pipe, we are using the same pipe. They are using the same diameter of the pipes, but we are differentiate between them in the number of the pipes. Now, means 0.463 if I have n number of the pipe. Let's try 2n, two pipes of I'm using two pipes to deliver 0.6463. So then the diameter of each pipes there should be 550. So here's the case one. The case one, if I have this is water, river, this is
Sir?
a sump, tank. So the water is coming through two pipes, and the phi of each of them is 550 millimeter. Now there is another case. You can use three pipes just to send water from this part to that part. So if I have using three pipes, you need to have to use smaller diameters. Smaller diameters about 450 millimeters. So either you will use two of 550 or three of 400. If I'm using four, there will be 400. So in emergency, we say two pipes is okay, but we should have 3 ones because we need to check for emergency. If you are using here 3, now it will be 3 plus 1 will be 4. So I advise you to use an odd number, not to go with the even number. So this is the odd number. So it means 3 pipes will be enough to deliver 0.463 meter cube per second from the river to that tank, and the diameter of each of them will should be 450. Now it's time to check if these diameters are correct or not. How to check this one? We have to check the velocity. We assumed a velocity, but now we have to check them. Now, actual one, sorry. Yes.
How do we know that the area of one pipe is 0.159? Because we already found the area required.
Yeah, we found that we found that if I'm using if this is the equation. This is the pipes numbers. This is the pipe diameter. So if you are using two pipes, you have 0.463. Now you can find from this one diameter of the pipe that's needed to cover that area. If you are using 3, then find a Q for that 3. Sorry, 5. This is not Q. This is diameter. This is diameter.
So you put 3 instead of the n?
Yes, and check.
0.
Yeah, try when I'm trying 3. 3, so I will see if this is 3, this is 400. So how much will be the diameter of this pipe? You can find this.
It is
0.463 divided by 3 times 4 divided by pi, right? This will be d squared. 4 times
There,
0.463 divided by 3 divided by,
so the area required, it's equal to n multiplied by pi over 4 multiplied by diameter.
yeah, this is area of 1 pi d
Okay.
square.
So
This
then,
is not a cube, but by the way, this is not a cube, this is d. This is diameter.
yes, okay, okay. I got
So
it.
the result, if I'm using 2 pi, if I'm using 2 pipes, I'm using 2 pi, the area, the diameter that will be needed through the equation is 0.443 meter, right? So you can
Yes.
say 450 millimeter is the diameter of the pipe. So if you are using 2, you need to have those 2 pipes, each of them, the diameters of each of them should be 450. Now, what if I use 3? So 0.463 is equal to 3 times pi over 4 d square. Means that d here is 0.463 times 4 divided by 3 pi, all equal to d square. So d in this case will equal to 0.463 times 4 divided by 3 divided by all 4. Take the square root. I think
It's
it's
0.443.
again 4.453. Yeah. I think we have a problem here
Yes.
somehow. Yeah. Okay. I mean, I'm sorry. We no. In the first case, we have to use 2. If I'm using 2, means this is not. This is 2, right? So 0.463 times 4 divided by 2 divided by pi will come, and take the square root of the answer will come. Yeah, this is, in this case, pi diameter is equal to 5.543. If I'm using t equal to 2, so 550, it means that 550, 2 pi's of 550, or 3 pi's of 450. So I think this will be enough for our case. Okay, is that clear?
Doctor, my question is, how do we get the area of one pipe is 0.159 meters squared?
0.159. How did you get this one?
Yes.
Yeah. In case that, so we agreed to use 3. Okay. Then the phi, or the diameter of that one, it should be 450, right? So
Yes.
in this case, area of each pipe is equal to pi d square over 4. Am I right? Which is equal to how much? 0.45 squared multiplied by 3.14 divided by 4.
You're not using the 3, right? Because we are talking about area of one pipe.
This is area of 1 pipe.
Gotcha.
So the area will become 0.1589 meters square. Means 0.159. So now, after I will decide on which number of the pipes is needed, then I will agree with having 3 pipes. The pipes each of them should have 450 millimeters diameter. Means area of 1 pipe is 0.195. It's time to check which I have to check. I have to check the velocities. Now the V actual means the real V is the Q divided by velocity in the pipe. Now we have the velocity. Here's the maximum monthly, Q maximum monthly. Q maximum monthly is equal to 0.6, 6 how much? 48, right? This is for 3 pipes, right? So for one of the pipes, I have to divide this 0.648 by 3. This is the number of the pipes that are. Then I have a velocity in every pipe. Now I have a Q in every pipe. Now Q divided by the area of the pipes. This is meter cube per second. This is meter square. I will get meter per second. Will be the velocity, and this velocity should be less than 1.5 meter per second. So I'm safe in this part. The minimum velocity, or the velocity minimum, it will occur when you have a minimum flow. Minimum flow, it will be, we have the Q minimum. The Q minimum is 0.324 meter cube per second. This is for 3 pipes. Now, so for one pipe, I should divide this one by 3 to get Q in each pipe. And divide by the area of each pipe, I will get a Q minimum in each pipe and velocity minimum in each pipe, which is now 0.68. It's greater than 0.6. Then it's okay. Now, the last thing that I have, if I have one of the pipes damaged, now I should use one less than the available ones. We have 3 pipes, 1 broken, so n minus 1, it means 2. So I will use the maximum Q, which is the maximum monthly, divided by 2 divided by area of each pipe. I will get the meter per second. Now it's 2.04 less than 2.5 meter per second. This is now, again, the test is okay. So the answer of this question, we need only 3 pipes, and those 3 pipes diameter should be 450 millimeters each.
Doctor, can you please repeat, how do we know that we need 3 pipes or 2 pipes, for example?
Yeah.
In which case?
Yeah, we have the total required area of the whole pipes. Now, the whole pipes need to have a Q maximum monthly divided by V. This V, I assumed it. I assumed it should be between 1.6 to 1.5. So, sorry, it will be between 1 to 1.5. I will assume 1.4 meter per second.
So that means it will not be given.
In the beginning, we should assume a velocity in every part.
Okay.
Now we have maximum monthly Q divided by this V. I will get the total area required for the whole number of the pipes, whatever they are, how much they are. So this is the whole needed area. Now I have the whole area, and this area will be the number of the pipes times an area of each of them, right? Now you have to try. Start from 2, 3, 4. 2, 3, 4, and they should not be less than 2, and you have to start checking for 2, 4, 3, 5, 4. If you are using 2, you need to have a pipe diameter of 550. If you are using 3, then you need 450, and if you are using 4, then you need 400. So you can decide for the 3. And by the way, you can check for four pipes and each of them 400. But when you are using this one, you have to go with the next 3 step, which is the checking step. The checking step is, now let's say you agree on 3. So now the 5 diameter required for each of the pipes are 450. It means that this is the 5 area of each of them. Now the V actual is equal to the maximum monthly Q divided by 3, which is now will become number of flow in each pipe, divided by area of each pipe. Will get the velocity in each pipe. This is the actual velocity. And you can see it's less than 1.5. Then you can go say, okay, what if I assume that, what if I go with this one? So if I go with the number of the pipes can be 4, so what will happen here? What the checking will be here. Instead of 3, we will use 4 pipes. And actually, will be 405 by
The area will be
square
changed.
over 4, which is sorry, which is 0.4 square times pi divided by 4. It's equal to, in this case, it will become 1.1225 or 6 meters square. So if you are using 4 pipes, so the area of each pipe will become 1.25 meters square. So what will be happening here? You are using, instead of 3, 4, you are using here, instead of 0.1, it will be 1.26. So let's check this.
And that the answer would be 1.285.
1.285, which is less than 1.5, which is okay.
Okay. Yeah.
Now, minimum, you have to check now for the minimum. This is also become 4. This will become 0.126. So let's check with this one, 0.32.
This
4
0.6
divided by 4
Wait.
divided by 0.126. Now, you can, it's 0.64, right?
still okay.
Still okay. Now, what we'll have here, you have 3. This is 0.126. So let's check 0.648 divided by 3 divided by 0.126. Yeah, it's also 1.7.
It's okay.
1 meter, which is okay also for me. Okay, so 4 is okay, 3 is okay. Now it's based on you. You need. By the way, don't miss. More pipes means more pumps. So each pipe should be connected to a pump, because what we are going to do, we are connecting. The water is coming from this side. With the pipes, we'll go here, and there will be pump here. Pump. Okay. Now it's up to you. You need to go with the 3, or you need to go with the 4. It's up to you. Now this was for the pumps, for the pipes. Now it's time to design for the sump tank. What I mean by the sump tank, this is the sump. This is the area or the tank that there is pumps inside. So we did with this one, pipes. We have done with this one. Now it's time to design for this tank. Okay, I will give you a rest, okay? And we will start within this 10 minutes, okay? Hello?
Okay, sir.